Oh, and a 50 mil graduated cylinder.
Cool.
Okay. So we want.
I'm very glad the door's on that side.
We got the small speaker.
What? No, we share a door.
Yeah.
That guy. Copy what everyone else has up.
Chose a pretty lady, so
Alright. So you should have the little tiny beaker. I think everybody's got a 50. Might have a 30. The little tiny Erlenmeyer, I believe that is also a 50. Your 10 mil graduated cylinder should be the smallest one. Your 50 mil graduated cylinder, that's sort of the middle sized one. And then your wash bottle is that sort of white squirty thing. Looks like it has a little bird beak on the front of it. That way we've got everything out that we need for today without having to kind of go in and out of the drawers all day long. You know.
anything that we do, don't be scared to just check me and triple check.
Okay.
Go away.
So,
Wow.
Yeah.
Are you having some
No,
technical
yeah.
issues?
we're going to kind of go through a lot of this lab sort of collectively, do a little bit, come back, kind of talk about it, do another part, come back, talk about it. We won't necessarily do that every single time, but for the first couple of labs, we'll kind of keep it as a group so everybody kind of keeps on task with what we're doing. We don't lose anybody. It also prevents me from having to say the exact same thing 37 times. So that helps a lot. So today's lab is just about making measurements in lab. We're going to use the bounce, we're going to use the graduated cylinders, how to make measurements, making sure we have the right number of significant digits. But then when we start doing calculations with those numbers, how do we deal with the digits that we get with those answers? So the very first page talks about two different things, accuracy and precision. And we often use sort of this dartboard analogy when we talk about accuracy and precision. And so if we've got our bullseye in the center of the dartboard, right, and we throw 5 darts, if we are accurate, where should the darts land?
Close to each other.
Okay, close together and where on the board? In the center, right? So if we have all 5 darts kind of close together in the center, that means we're accurate, right? Well, we have another term that we use when we're talking about our instruments, and that's called precision. And there's 2 different things that we mean when we talk about precision. One is the precision of multiple measurements. And what that means is if I throw my darts at the dartboard, how close do I get them to each other? Okay? So that second dartboard, those 5 darts are very precise. I can basically hit the same spot in the dartboard over and over and over again. But is it accurate? Am I anywhere near the bullseye? No. So that happens to us a lot in science. We can repeat the same value over and over and over again, but it's not really the right number. That tells us there's probably something wrong with our experiment, or we need to make a correction. We can add a correction factor that says, okay, if I'm constantly off by that distance every time, well, I can make a correction for that in my calculations and correct for that little error. What we don't want is this, right? Are those 5 darts precise? No. Nowhere near each other. Are they accurate? Nope. Nowhere near the right answer. But what if I average them? Where's the average of those 5 darts going to be? Right in the middle. Right? If I average, I'm going to end up right there. So I can take really awful data, take an average and go, oh look, I got the right answer. Right? But my measurements weren't anywhere near where they needed to be. So we need to be kind of aware of kind of how we can manipulate our numbers a little bit. The second thing that we talk about precision, is the actual measurement that the tool that we're using can give us. So I want you guys to look at your 10 mil graduated cylinder and your 50 mil graduated cylinder. And I want you to look at the distance between 1 milliliter line and the next milliliter line. So on the 10 mil, that could be between like 7 and 8. On the 50, that could be between like, say, 40 and 41. Okay. How much space is there between those 1 milliliter markings on the 50 mil graduated cylinder? Are they pretty close together? Yeah. Could you estimate between them? Could you estimate, say, 40.5? I'm halfway between those two lines. Do you think you could probably do that? So we say that this 50 mil graduated cylinder has an accuracy of plus or minus 0.1 milliliters. I could estimate to the 10th place. I could estimate between those 1 mil markings, right? But look at your 10 mil graduated cylinder. What do you notice about between 7 and 8? Are there more markings in between? How many? 10. So that means between 7 and 8, there's 10 more little markings, right? So that means the markings here, right, I could get 7.5, and then I could estimate between 7.5 and 7.6, because those are lines on my actual graduated cylinder. So for the 10 mil graduated cylinder, we would say that precision is plus or minus 0.01 milliliters. I could go all the way to that second decimal place as my estimated number. Okay? So if I'm measuring 10 milliliters of liquid, which tool should I use? The 10 or the 50? Which one's going to give me a more accurate measurement of 10 milliliters?
10 millimeters.
The 10 mil graduated cylinder, because that goes to the second decimal place. It's a more precise measuring tool. There's more values in that measurement. This one would give me a measurement of 10.00 milliliters if I was right at the line. This would only give me 10.0 milliliters if I was right at the line. I get that extra digit by using a more precise tool. So we've got two different things when we talk about precision. So some questions there on the bottom. It says, given the measured data, 12.02 grams, 12.03 grams, and 12.01 grams, and the actual value of 18.634 grams, describe both the precision and the accuracy of that data. So the three data points, are they precise? Are they close to each other? Yeah. So they're very precise. We can get a repeated value within a very small margin every single time. But are they accurate? No, they're nowhere near the right number. So we would say that those data are precise but not accurate. Okay? So what's a factor that could cause that type of inconsistency in the measurement? So these are mass measurements. You guys are going to make some mass measurements today. We're going to go into the balance room. You're going to use the balance. You're going to put your object on there, and you're just going to read what's on the balance. So if I go in and I measure this object 3 times, I get virtually the same mass every single time, but I'm nowhere near the right answer. What could cause that?
Calibration error.
Yeah, probably a calibration error. There's something wrong with the balance, right? Some people might say human error. Well, would human error give me precise data, the same measurement every time? Or would human error be more random? What if there were air currents blowing around the room, pushing on the balance pan, kind of fluctuating the balance? Would I get precise measurements that way? No, they'd be all over the place. So often when you have that sort of precise but not accurate data, there's something wrong with your measurement. There's something wrong with your tool. In this case, in the balance, it's probably a calibration error. The 0 point on that balance probably isn't in the right spot. It means we need to do some maintenance on that balance. So when you do have problems with your data, one of the things we want to think about is, where did that error come from? Is it something that I did that I could fix, that I could control? Or is it something with my tool and I need to deal with a better tool or fix my tool, right? So try and figure out where that error is coming from. All right. So the first thing that we're going to do today is measure mass. And we're going to do that by measuring some pennies. Okay? So you guys are going to take 5 pennies. There's a whole pile of them over there. Just pick out 5 pennies. And you're going to weigh each of these pennies individually. Record each of their masses one at a time. And then you're going to do a 6th measurement where you put all 5 pennies together and weigh them sort of collectively. Okay? The issue is when we go into the balance room, these pennies are pretty small and they're pretty flat. And if you just set them on the balance pan, you could easily get their mass, but what would you have to do to pick that penny up?
Push down.
Could you kind of grab it like a claw and pick it up really nicely? Or do you have to sort of push down on it to lift it up? Yeah, you'd have to sort of push down and slide it. And we don't want to do that to our balances. Our balances are accurate to 3 decimal places. So we don't really want to put any undue stress on that balance pan by pressing on it with our hands. That's what your little tiny beaker is for. Okay? Can I borrow yours for a second? The little piece. So what you guys are going to do is go in, and our balances have little doors on the sides. Okay? Open the little doors, put your empty beaker on the balance pan, and then close all the little doors. Then on the bar on the front of the balance, there's a label that says 0/T. That stands for tare or 0. And what that tare function does is it zeroes out the mass of whatever's sitting on the balance. So it's going to basically make this beaker part of the balance pan. So it zeroes out that mass. Then you can take your penny, drop it in the beaker, write down the mass of the penny, and now when you go to pick it up, you can easily lift that beaker up without putting any strain on the balance. Take the first penny out, put the second penny in, put it right back on the balance pan. Okay?
Do you need to zero it out at the time?
No, you shouldn't have to. You can check it to make sure it's still 0 before you put the next one, but you shouldn't have to. It should maintain that after a while. The only issue that I'm going to tell you is what's happening as I'm holding this beaker. I'm putting fingerprints all over it. Do fingerprints have mass? Yeah, they do. Fingerprints arise from when the oils on your skin transfer to something else. So if I sit here and I'm like holding this beaker, I'm putting all kinds of fingerprints all over this beaker. And if I do it enough times, I might put enough fingerprints on here that our balances can actually measure that mass change from those fingerprints. Our balances are that sensitive. So one of the things that we do anytime we're going to weigh something is over there in that orange box over there we have gloves. If you handle something with gloves, then you don't leave those oils behind. Okay? So highly recommend whoever's kind of handling the beaker, put some gloves on. That just avoids the fingerprint problem. So you're going to weigh each penny one at a time, then put all 5 pennies in the beaker and weigh those together. So on your little data table that you have here, it says mass of penny, 1, 2, 3, 4, 5. Then it says collective mass of 5 pennies. Okay, so those are where those masses are going to go. Right above that where it says question 3, it says what is the precision of our top loading balances, right? So we were talking about precision with our graduated cylinders here, right? Well, are there markings on our balance that we're reading between? Or are we just looking at a number? Just looking at a number. So who's doing the estimating? The balance. The balance is still estimating plus or minus that very last digit. Okay? So we're not making that estimate, but the balance is doing that. So since our balances go to the 3rd decimal place, they're accurate to plus or minus 0.001 grams. That would be the precision of our balance. We call them milligram balances because they measure to 1 milligram. Okay? So that's that question 3. What is the precision of our balances? That's where we would put that number. Then you're going to weigh the pennies. So that's the first thing that we're going to do. I'm going to stop and have everybody go do that. There are some pennies in the bowl on that back table. There's also some pennies laying out on a paper towel. You can go ahead and use the ones on the paper towel as long as they're dry. If they look like they're wet or moist at all, don't use them. Okay, we want to use dry pennies before we go in. So the balance room is back through here. There's actually doors on either side of the room. There's balances all the way down the whole line. You can choose whichever balance you want. Just whichever balance you choose today, there's a number on that balance. You're going to use that same balance all day long. Okay? The 151 class is in the other classroom. They might be coming in and out of the balance room as well, so just kind of keep an eye on them as people are going in and out. Okay? So 5 pennies in your little tiny beaker. Go ahead and measure those masses individually. Measure them collectively. Follow the directions that are on that.
Okay,
And as soon as you guys want that, I'll let you.
Grab that. Yeah. I'll grab that. Pick out a scale. Set it all up.
It's a lot easier to grab 5 when everyone's not going like 1, 2, 5. If you have 5 pennies in your pocket and you want to use those, you can use those. Ours are just a little more used.
So did you zero it out?
Yeah.
And so did you zero it out?
I just put it in and hit it.
So, now it's zeroed out.
Right, 2.502.
Yeah, hold on, I was thinking.
3,
Yeah, do.
2, 4, 3, 2.
Let's do 2, yeah. Did this one.
Stealing these pens.
3.082. Four.
Do them all individually.
I got all of them, right?
Keep it on here.
Right? Is that it?
Yeah.
Can I check those penny sacks? Get it going.
And then take these. Is that it?
Yep.
Sorry.
Excuse me.
Yeah, you'll need to keep your same 5 pennies. Okay. So keep your pennies when you come back in. Don't come back out. Keep your 5 pennies out.
See, like this one, this is this one.
All
This
right.
one's curved, that one's
Yeah.
not, you know?
Well, when we did that one last, the next shiny one?
Was it?
I think it was.
It was the latest. The-
0.094. Yeah. It's funny that it weighs more. Only the one that's covered in card.
I know. I know.
Big
Sure.
That's not the sum.
No, that was our collective. This is
Okay.
going to be different. I think that's the
Yeah,
whole point
these
of
have been
it.
divided.
And now we put all of them in there, right?
I think we just add them all up back in the classroom.
Yeah, we have to do the collective mass of the 5 pennies.
Alright, so those of you that have come back in, you can start working on questions 4, 5, and 6. It says determine the sum of all 5 pennies by adding the individual masses together. Record that sum. Determine the average mass of a single penny by using the collective mass divided by 5 to show your work. And then we'll talk about question 6.
And then 2.510.
So your average mass should be using the collective mass of your 5 pennies together. The sum should be your 5 individual masses added together.
Okay. Or you want to use mine? I mean, I don't care. I'm just thinking of
Keep your 5 pennies because we're not done with them yet. So make sure you keep your 5 pennies
this up.
with you. We're not done with those pennies yet.
Just a different
Hang on.
answer from what my calculation was. You hear the whole, it's just gonna add it again. Yeah.
You just gotta do that up here.
Upload it.